Good evening, everyone. Thank you for joining us. I'm sorry that we don't have a bigger space for everyone, but it's a pleasure to have everyone. Are all the seats filled? Are there any empty seats? There are no empty seats. I'm not going to ask people to sit on laps. I don't think that's within the challenges here. So thank you for joining us for our March Stargazing lecture. I'm Dr. Cameron Hummels. I'll be your MC for this evening's event. I'll lay out the schedule and what to expect for tonight. So I've got a few brief announcements, and then I'll introduce our speaker, who's going to talk for roughly 30 minutes. And following that, we'll have a brief Q&A, 5 minutes or so with the speaker. And then it'll be the choose your own adventure portion of the evening. You can stick around in here. We'll have a panel Q&A composed of the speaker, myself, and two scientists from the Planetary Sciences Department here to answer questions on a variety of different topics, whatever you feel like asking. It could be related to the content of the presentation or questions about astronomy or space science or planetary science or whatever. So we'll try to address those. At the same time that our Q&A panel is occurring in here, we have telescopes that are being set up outside right now. As you probably saw, the conditions are not perfect. There's some high cirrus cloud, but we have two really bright targets in the sky tonight, Jupiter and the moon, which should be visible through the telescopes. So hopefully some wind comes and blows those cirrus clouds away. But both of those events will go on for about an hour until 9:30, 9:45 or so. So you can feel free to go back and forth, listen to a couple of questions on the Q&A panel, go outside. If everyone rushes out to look through the telescopes, there will be lines on the telescope. So it may encourage you to stick around for a few minutes to let that die down a bit. So these events typically happen once a month. They feature a different Caltech professor or graduate student or postdoc who speaks before the audience on a variety of topics. We do live stream and record this. We're live streaming to YouTube right now. Hi, YouTube audience. So if you're interested, there's recordings of our last 10 years of these events online on various different topics from various different esteemed scientists online. So I encourage you to check it out. Our next one of these, there's going to be a 1-month hiatus. I'm traveling next month, but our next one of these will be Friday, May 30th. And I don't yet know who it's going to be, but I think it's going to be about black holes. So for what it's worth, if you're interested, just check back. We have a website. It's on the Caltech calendar. It's on various social media platforms as Caltech Astro. However you found out about this one, you should be able to find out about the next one. We also have a mailing list. But in addition to these events, we also have something called Astronomy on Tap. That's kind of a sister series. Some cheers. It's fun. It's super fun. It's at a bar in Old Town, Pasadena called the Dog House, an outdoor kind of beer garden space. And it features two 15-minute public level science presentations from different scientists, not just from Caltech, but also from JPL, from Carnegie Observatories, from Griffith Observatory, from UCLA, various different science institutions here in town. And there's also astronomy-themed pub trivia. There's typically telescopes. Sometimes we have live music. So if you're interested, those events happen, again, typically once a month on a Monday night. That's the only time they let us use the bar. It's also open to all ages, so families can come. There's no challenges there. And our next one of those, I think, will also be in May or early June because of this travel that's coming up. I should also mention that there's going to be a bunch of events in the middle of June. The American Astronomical Society, the kind of national group of astronomers from all around the country, is going to be having its semi-annual meeting in Pasadena at the Convention Center in the middle of June. And so we'll have a bunch of astronomers in town, but we'll also have a bunch of public outreach astronomy activities. So we'll do 3 Astronomy on Taps that week, Monday, Tuesday, and Wednesday, featuring scientists not just from Caltech and Pasadena based, but also from other institutions who will be in town for that. And we'll also have a City of Astronomy Science Festival happening the Sunday before that, which I think is June 12th or 13th. I forget the exact date, but this will be a science festival lasting all day on a Sunday at the Convention Center, featuring all manner of different science demonstrations and activities that people can participate in from Caltech as an institution, but various science institutions around Los Angeles. And of course, as all of these events, it's free and open to everyone who wants to participate. I think those are all of my announcements. So let me introduce our speaker tonight. Our speaker grew up in Lebanon before pursuing an undergraduate degree in physics at Charles Fourier University in Grenoble, France. He then pursued a master's in engineering at Grenoble Institute of Technology before coming to the US and coming to Caltech, where he pursued a master's and PhD in electrical engineering here. After finishing, he stayed on as a postdoc and then eventually was named a faculty member in the institute here and has remained basically ever since. And I don't mean that in a bad way. He's jumped between Caltech and the NASA Jet Propulsion Laboratory over the last 50 years, having positions at both, between professor here and a researcher at JPL. And in 2001, he was named the director of the NASA Jet Propulsion Laboratory, where he remained for 16 years, guiding NASA through many of its most significant accomplishments and discoveries. He was the director while there were, how many was it? 24 different missions that were launched. Really notable ones like Spirit and Opportunity, two of the rovers going around on the surface of Mars, as well as Curiosity, another rover that was on Mars, Mars Reconnaissance Orbiter, which has revealed a ton of information about the surface features across the entire surface of Mars, but not just Mars, many astronomy missions, astrophysics missions, Galax, which is a UV mission, which was PI'd out of this department, New Star, which was an X-ray mission. So revealing what the sky looks like in X-rays, revealing what the sky looks like in UV. The Kepler mission, which was one of the most significant missions to discover exoplanets that we've ever launched. Juno, which is still in orbit and doing amazing science around Jupiter. I mean, the list really goes on. And he has a ton of accolades, and I'd be here forever if I went through all of them, but just recognize that this man is a very significant scientist and contributor to the field of astrophysics and space exploration. And the point that I just want to end on here is, you know, not only has he done really amazing things, but he's considered pretty much the most beloved director of NASA Jet Propulsion Laboratory, because he didn't just have vision to guide this institution and space exploration on a really significant path forward, but he was very approachable. He walked the halls and talked to all the scientists, unlike some of his predecessors or subsequent directors. And for that reason, he's quite beloved. So I'd like you to please welcome Dr. Charles Elachi.
Yeah, I turned it off. Okay, can you guys hear me well? Yeah. Okay, well, good evening, everybody. I'm particularly delighted to see so many young people. You guys will be the future employees at Caltech or JPL, hopefully. I know things are challenging now, budget-wise, but you know, things come back up, so I won't worry about it. Now, before I start on my talk, I usually like to get people in the right mood. So I'm going to tell you a story about Caltech faculty. So after many years of lobbying, St. Peter convinced God to connect to the internet. So God sat down one day and said, okay, who should I send an email to? Oh, I'm going to send an email to the devil. So he sent an email, hi there, how are things down there? And immediately he gets back an email, things are great, it's 71 degrees here, I'm having my martini, I'm reading my comics. So God got really irritated and said, how could that be? It's supposed to be hot down there. And the devil sent back a message, well, I found these Caltech faculty who really are good at thermodynamic, and they really wired the place here and they air conditioned it. So it's really great. So God got really irritated. He sent back an email and said, wait a minute, all Caltech faculty are supposed to be in heaven. How about if we send them up here now? And the devil said, no, I'm not going to send any of them because I really need them here for the air conditioning. So God got really mad and he sent back an email and said, send them now or I'll sue you. And the devil sent an email back, and where are you going to find a lawyer? They are all down here. So my wife has heard it many, many times, and she's still laughing. So anyway, what I'm going to do today is to really talk as the type of space exploration and discovery. And it's amazing what has happened in the last 60 years during a lifetime. I remember very clearly, I think I was your age when Explorer was launched. So this was the first time we put something in space. I mean, Sputnik and Explorer. And look where we are today. We have been to every planet. We have landed on a number of them. We have rover. In astrophysics, we have really advanced, the frontier of what's happening in the universe, how it came about. And in earth science, we regularly are monitoring what's happening on our planet. That's all during a lifetime. So I can spend the whole week, telling you about all the discoveries and so on. But I thought I'm going to just pick few things which either I was directly overseeing when I was director at JPL, or I was principal investigator on them. And it will give you a flavor, of the kind of discovery. And I will tell you a little bit of some things which were happening behind the scene, in some anecdote. I have to watch my jokes a little bit with the younger people here, but I'll give you a flavor of how things. So I'm going to start by talking about Mars first. And the reason is I always get the question, which one was your favorite mission when you were director at JPL? And my answer usually is like people asking me, who's your favorite daughter? I love all of them because each and every mission, you learn something new from it. And that's what exploration is about learning new things. But when you look at the drama and the excitement, no question the Mars, add a really twist as you will see in some videos. And I'm going to show you a video about the landing, even that I'm sure many of you probably have seen it. But every time I show it, my heartbeat goes up by 50% because of the excitement that happened in it. So just to give you a background about Mars, Mars is kind of similar to Earth to some sense. It's about a quarter the size of Earth, which means that the land mass on Mars and the land mass on Earth are about the same, if you take the ocean away. So it's a pretty big place. And as you will see in a minute, there is a lot of similarity in the geology. I can show you some pictures and tell you these were taken in Death Valley or in Mojave, and you kind of will believe me, even that they are on Mars. Mars has an atmosphere, but it's 1% the Earth's atmosphere. So it's very, very, very thin. And you'll see in a minute why I'm telling you that. It has polar caps, like what you see down here. And it has seasons on it. The year on Mars is roughly 2 years, on Earth. That's how long it takes it to go around the sun. The day on Mars is roughly the same as the day on Earth, give or take few fraction of an hour from it. So I'm going to take you and show you how actually we land on Mars. So we have done 5 rovers on Mars. We have landed more often, but we have had 5 rovers on Mars. And the first one was done in the late 90s. But the large rover Spirit, Opportunity, Curiosity, and Perseverance were done in the last 2 decades. And as we speak today, as we're sitting here, we still have 2 rovers actually exploring Mars. Think about it. It's amazing that here in your neighborhood, you have people, either your neighbors or your friend, which participated in doing that. So I'm going to take you to the mission control center the night we landed Perseverance, on the surface. And think about it, as you are coming in at extremely high speed, and you have to slow yourself down in 5 minutes or 6 minutes, so you can land very softly, on the surface. And basically what we do, first we start by having the heat shield, which will slow you down, similar to like when you are driving fast in your car, you put your hand out and you feel the pressure. So that's how heat shield work, but they are much faster. The speed is much faster. Then we'll open a parachute, supersonic parachute. Then we fire retro rockets. Then as we get few tens of feet above the surface, we hover and sky crane the rover very slowly down to the surface. And all of that has to work perfect. And you cannot joystick it because it takes 10 minutes for the signal to get to Mars and come back. So it all has to be done autonomously and tested ahead of time and so on. So it's a little bit nerve-wracking, as you will see, in the video that I'm going to show you. And particularly on Perseverance, the last one, we had lots of cameras. So you are going to be seeing actually a real-time picture of what's happening on Mars.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute
watch
deploy
the faces
and to
of the
roll over
people.
to give the radar a better look at the ground.
People. maybe not too different for the ages of some of
Applicant
the
indicates
people.
shoot deployed.
So I said first that
The navigation has
looking up to the
confirmed that
parachute.
the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And then this one looking down,
shield
and we
set.
drop the heat shield.
Perseverance is now slowed to
And this is
subsonic
Mars. This is
speed,
real.
and the heat shield has been
So this
separated.
is not Hollywood
allows
doing this thing.
both
This
the
is
radar and the
actual,
cameras to get
real.
their first look
If you,
at
like
the
if
surface.
you are, if you
Current
travel to
velocity
Mars
is
one day, that's
145
what you will
meters per
be
second
seeing.
at an altitude of
Coming
about
down.
10
So
nine
every
and a half
time I look at
kilometers
it,
above
I
the
think to
surface.
myself, this is another planet. We are landing on another planet. That's what's amazing about it. So you see the heat shield going down, and then we had to maneuver to avoid hitting the heat shield. And then you will see it kind of wobbling back and forth. That's because we are on
Nav
a
filter
parachute.
converge. Velocity
coming down in
solution
the
3.3
parachute.
meters per
There you
second.
go. And then we
Altitude
wanted to land in a
7.4
very
kilometers.
specific
Now
place.
has radar lock on
So
the
we had
ground.
to
Current
kind of move it.
velocity is about
And
100
it had
meters
to
per
do with all
second,
autonomously.
6.6
To
kilometers
move to
of the
land in the
surface
right
of Mars.
place.
Perseverance is continuing to descend on the parachute.
No,
We
except
are
for the
remaining
craters that looks like
on
Mojave.
the
if you were
initialization of
flying
terrain
over
relative
Mojave.
navigation and subsequently the priming of the landing
And see
engines. Our
sand
current
dunes?
velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Now you can go on the JPL website and you
Okay,
can
valid.
access.
We have confirmation that the land
of
division system has produced a
to show.
valid solution and part of terrain relative navigation.
Priming. PBA is nominal.
We have priming of the landing engines.
And the way we know the distance, there is a radar on it, which measure
Back
actually
shell
like
set.
the
Current
policemen when
velocity
they,
is 83
kind
meters
of
per
measure your
second at about
speed, we can measure the
2.6
distance.
kilometers from
And
the
that's
surface
what
of
drives a
Mars.
lot of the
We have
activity on
confirmation
the
that the back
spacecraft.
shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN 50 Bravo.
We have completed our terrain relative navigation. Current
And
speed
in a
is
minute,
about
you'll see when
30
we fire
meters
the
per
retro
second,
rocket,
altitude of about
you'll
300
start
meters
seeing the plume,
off the surface
or the
of Mars.
dust coming from the surface.
We have started our constant velocity accordion, which means we are conducting the sky crane,
And now you see us
about to
kind of
conduct the sky crane
dangling
maneuver.
the rover on a rope. That's the
Sky crane
bottom
maneuver has
one. The
started.
upper one is looking up and the bottom one is
About
looking
20
down.
meters off the
So we
surface.
sky crane the rover slowly to the surface. And once it touches the surface, we can sense that, and that will cut the
Looking for
umbilical
signals from
cord.
MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Let me tell you, it's extremely tense being in the Mission Control Center. I've lived through 3 of these rover landings and some fixed landings. It's really, it's very tense, but also it's very exciting because the people who are sitting there, they have been working on this probably for 8, 9 years, and everything depends on those 5 minutes. Either you are a hero at the end of the 5 minutes, or, then you go home and kick the dog or kick the door, it didn't go well. So the key thing is as soon as we land, on the surface, very quickly we start sending images. Oh, sorry. Let me tell you why we were maneuvering to land at correct place. One of the key objectives of what we are doing is to see, was Mars inhabitable in the past, or is it inhabitable today? And based on a lot of data that we have gotten over the years, we believe that when Mars formed, roughly the same time as Earth, Mars was much more wet than it is today. It was very similar to Earth. And for some reason, which there are different explanations, the water on Mars kind of either froze or evaporated. And here on Earth, we still have a good environment, that we have here. And there are a number of explanations to explain why that happened. So a key question is, if Mars was similar to Earth at the beginning, a few billion years ago, could have life started on Mars similar to what started on Earth here? And if it did, where is it? And what does it look like? If it did not, why not? Why was it so different than what we have in here? So we wanted to land in a place which kind of looks like the rivers were there. because that might indicate that that's more likely that you can find some indication of habitability. So you can see what looks like a river here, coming all the way here, and then that's like a delta. So this looks like the Nile Delta or down in Louisiana, in Mississippi deltas. So we wanted to land very close to that place so we can drive around and do the sampling, in that area. And one of the key objectives of the latest one is to actually collect samples so we can bring them back at some future time. And that's what the pictures on the surface look like. This is the back of the rover. We always make sure we have JPL name, and Caltech name is under it. Also you can't see it very well here. And the rover, particularly the latest rover, is about the size of your SUV. But the interesting thing about them and the challenge is they have a chemistry lab similar to what you find at the Caltech chemistry lab. All of it to be compacted, in that rover. So it has X-ray machine, to measure, the sample, similar to what your dentist use X-ray to look at your teeth, except a lot more expensive. We have a gamma ray instrument. We can grab sample, put them in an oven and heat it so we can determine what's the composition. There is a laser which zaps the rock and see what's being evaporated so we can determine their composition. And all of that is sitting in that rover. So that's a big challenge of how do you compact this, have the appropriate power to do it, and then collect the data and transmit it to Earth. Now, the way these things are powered, you see here, that's what we call an RTG. And basically what it is, we put pellets of plutonium, and as the plutonium decay, it generates heat. And then from the heat, we have what we call thermocouples, which generate then electricity, for it. And it runs on about like 150 watts. So it's like a couple of bulbs at your home. And that's what runs the whole rover, all the instrument. Now we have batteries that accumulate the power in them, but it's run on a very small amount of power. And that's another picture. So usually as soon as we land, or very shortly after we land, the rover has an arm, has a camera. We press the arm and we take a picture. The rover takes a picture of itself. It's like when you get a new iPhone, you take a picture and you send it to mom. Look, mom, how good I look. So here we wanted to make sure that everything is looking fine. So all of this is being done very carefully, very meticulously in that. And these have a couple of scenes here, some of them from Curiosity, some of them from Perseverance. So this is a panorama. Again, I've seen many similar things, out in the desert here or around, in Mojave or Death Valley and so on. And some of these, I'm sure some people think there was inhabitants who live here. Some of them look a little bit too organized. But so far, we have detected organic molecules, but we have not detected life yet on it. But that will take a while, to most likely it will require bringing the sample back to Earth, to do that. That's another scene. Also, I just picked 3-4 scenes here to just give you a flavor of what Mars looks like. And this is a scene. So here you see a little more detail, of the rover itself. You can see the wheels. Now on Curiosity, what the engineers at JPL, they put a pattern on the wheel, holes, on it. And one day, I didn't know anything about it, but one day before we were launching, I went and I said, "What, these holes look like they have a pattern. What are they?" And one guy said, "Oh, that's the Morse code for JPL." So as we drive, we printed JPL on the surface. And they said, on purpose, we didn't tell you, because when NASA gets mad at us, you can deny that you didn't know, anything about it. And that's one other, picture of that area. Now, for me, this is probably the most iconic picture that in my mind. Some of you who are my age remember the one on the left, that Neil Armstrong footprint on the moon. This was a huge thing that we actually, now, it looks easy. But in the 1970s, that was a huge advance of actually sending a human to the moon. And that was his footprint on the moon. On the right, that's our rover footprint on Mars. So these are the two human, even that the rover is not exactly human, but it was done by humans. The two footprints which are on other planets or other solar objects. So that's why I think of it. And this quote, in here, that's, for the young people, you can take a note, about that. That used to be in my office on the wall, because that reflects on what JPL and what we as a country actually are doing. We're opening new paths, and at NASA. Now, one thing which was on this last rover, we added a little helicopter. Now you would say, well, what's a big deal? We have helicopters everywhere. My kid has one of these toys. Well, the difference is, as I told you, on Mars, the pressure is 1% the pressure on Earth. That's the equivalent of flying at 30,000 meters. That's 100,000 feet above the Earth. Nobody has ever done that because it's so thin. Matter of fact, the highest helicopter ever flown was about 1/3 of that height. And Mount Everest is about 1/4 of that height. So it was a real challenge. Matter of fact, to tell you the story behind it, I was at some event up in a place called the Bohemian Grove, and a speaker came, that was like 15 years ago, and a speaker came and started talking about drones. They were a novelty at that time, nobody had them. And I was so amazed by what they did. As soon as I came back to JPL, I called a group of people and said, well, can we do this on Mars? Look what I heard about. Can we do that on Mars? And first reactions, you are crazy, Charles. I don't know what you were smoking, but you are really, because it's like 1% the pressure on Earth. But in the typical JPL attitude, say, well, give us a couple of weeks. We'll go on and look at it. So they come back a couple of weeks after that and say, yeah, we think we can do it. So I gave them a little bit of money from discretionary, and then I had to go and convince now NASA to put it on the rover, because the rover was almost built. And let me tell you, now I know you are recording this, maybe you can edit it. I got the usual bureaucratic reaction, oh, it's too late, it's too risky, I'm not sure we want to do it. What if fails? And all of this thing, we never tried this before. Anyway, one thing I tell the young people, if you believe in something, never take no for an answer. If you really believe it, just keep making the case for it. So finally, NASA agreed, for us to put it. By then it was already built, so it was fairly straightforward to put it on. And we were nervous, and we promised this will be a technology demo. We will do 3 flights, and if they work, we declare success. So that convinced some skeptics, at NASA on it. So here you see that helicopter. And of course, we were sitting very nervous, to see it if it's going to take off. And there it goes. And this was being taken video from the rover, watching it. And to make a long story short, we ended with 74, I think. There might be some people from JPL here who remember better than me. I think we ended with 74 flights, so we promised 3. Now, people always tell me, oh yeah, you are JPL guys, you gold plate everything. Well, in the reality, we do very good engineering, on this thing. So and now you'll see it coming back and landing. Now, you'll say, what's the benefit of a helicopter? It really stretches your range significantly, because before we used to land and look at picture around us and sample. Then we moved to rovers. So we could go many tens of kilometers and really explore different areas. But still, rovers are kind of limited. You cannot go through a cliff. There might be a steep mountain to go over it. So a rover can a helicopter can allow you to go many tens of kilometers, even in principle, hundreds of kilometers. You can go down into a canyon and take pictures of the wall of the canyon. As a matter of fact, if you are keeping track of what's happening at NASA, literally on Tuesday, NASA announced, the new NASA administrator announced 2 major initiatives for the next decade. One of them is doing the lunar station, on the moon, and do exploration of the moon using like little hopper, using little rover like Cadre, if there is anybody here working on Cadre, and these kind of, to extend the stretch. Now, you cannot fly on the moon because there is no atmosphere. And the other initiative is called Skyfall, which is actually to send to Mars a mission which will drop multiple helicopters. So you can explore multiple areas, and they will have radars on them to sound and determine where is the ice below the surface. There will be potential future human exploration. So you can see just from this little crazy ideas, it opened a whole new domain for us to explore another planet. And as you will see later, almost any planet which has an atmosphere, we can actually send helicopters to. And these are some pictures taken from that helicopter. You remember that there was a back shell which was bringing the rover down, which flew, after we landed there, it flew away. So that's a picture of it because it went and crashed, and we don't use it, so it's not an issue. And this is a picture of the rover taken from the helicopter. So the rover and the helicopter were taking pictures, you know, for each other. Now, let me tell you one thing before I move away from Mars, just to tell you why I like to show this. After we landed Spirit, I think, I remember after successful landing, and we were very nervous, you know, about it. I went out of the mission control center, and it was in the evening. So it happened on that day that Mars was in the horizon. So I stood there for like 10 minutes and said, we just landed on that little star or that little planet. I mean, when you think about it, it's absolutely amazing. So next time you see Mars, which I checked, with Cameron, if we'll be able to see it tonight, it turned out it's not a good time for it. But by end of May, you'll be able to see Mars. So what I would suggest, take a glass of wine with your friends. You got a glass of water, not wine. And sit outside and look at it and say, you know, people around me here at JPL and Caltech, and we actually landed on that planet, and there are 2 rovers now which are roving and exploring like that. Just thinking about it, you know, I think it will make your heartbeat go up, because it's amazing what has been accomplished. Now, let me move to other examples. It's a picture of Saturn. We had a mission, which kind of was completed. It's called Cassini, which went and spent many years exploring Saturn. But the one I want to mention to you particularly is this satellite, which is a Titan, satellite, which is around Saturn. It's kind of a little bit bigger than our moon. And it's a planet where we didn't know at that time before we launched, what did it look like? Because it had haze all around it. So there were models of people saying it's completely covered with ocean. Maybe there is no ocean on it. So we put on that mission an instrument, which is a radar instrument. And the unique part about radar instrument is that because you use microwave, you can actually penetrate through cloud and actually be able to get the images of the surface. And because you use your own signal, it doesn't matter if it's day or night. So they can take picture, it's like the policeman can stop you if it's at night, or if it's raining or anything, they still can measure your velocity. And to our surprise, we found that Titan had a lot of lakes on it. And these are not like little ponds. These are lakes about the size of the Great Lakes, in the US. The only thing which is interesting, which make it even more interesting, that all of these lakes are made of hydrocarbon. So it's not liquid water. And it turned out, if you look carefully, there are rivers on it. So there is a whole you can call it hydrological, but that's not exactly correct. But a whole cycle like on Earth, where it rains hydrocarbon, goes in the river of hydrocarbon, go to lakes, evaporates. So we have a whole cycle like what's happening on our planet. Now, jokingly, I tell people, but there are signs everywhere that says no smoking. Because if you light something, the whole planet will blow up with all these hydrocarbons. So that's one thing. I was the principal investigator on that instrument. So I lived through it over many years. And one thing I want to mention to give proper credit, almost every instrument I flew, actually I had participation from either France or from Italy. So in almost all our mission, we have international, collaboration on this thing. The Italians are particularly good with radar instruments. And now what NASA is planning as a legacy of the helicopter I told you earlier, is to send a helicopter to Titan, because I told you it has an atmosphere. Now, Titan is a little bit easier than Mars because the atmosphere is roughly about the same pressure as our atmosphere here. So it's easier to put a helicopter in it, but it's even farther, so it has to be completely autonomous, and you have to generate power using RTGs on it. So this is called Dragonfly, and that will be launched, I think, in early 30s or late 20s and get there by mid 30s. Now, one thing also that reminds me of, in this business, you have to be very patient. You know, for instance, a typical, like when we did Cassini, from the time we started thinking about it until the mission ended was 30 years. So it takes, I mean, the solar system is big, you know, so and that's only the solar system. You know, if you want to go even beyond that, that's even bigger. So you have to be really patient, you know, in doing that. It gives you a little bit of job security, but yeah, some people spend all their career actually working on missions like Cassini. Yeah, I should have mentioned, like Mars take us 9 months to get there, 6 to 9 months. It takes us a couple of years to get to Jupiter, a little bit longer to go to Saturn, and so on. The other place which is very interesting is Europa. Now, this is a picture of Europa, and Europa is made completely of ice. And you see these cracks on it and this brown material. And when I say ice, I mean water ice, similar to what you have in your cocktail. And basically, so the key question is, if there is ice, and when we look in more detail on it, we see what looks like cracks, like ice flows. It's a little bit like if you are flying to Europe over the North Pole, it looks like the ice flows that you have over the North Pole. And based on a number of data acquired, you know, gravity, magnetic field, we believe there is an ocean just below that ice. And as soon as it's a liquid ocean, and as soon as you say that, you wonder, could there be life, you know, in that ocean? If it's liquid water and there is organic material, could there be life in it? So one of the purpose of this mission is actually to have, and this mission is on its way now as we speak. It will get there in 4 years. One instrument, which is a radar instrument, similar to what I mentioned to you before, that I'm involved in it, and basically to measure how thick that ice is. And what we want to see is, are there thin, relatively thin areas, like a few hundred meters? So in the future, we can land and actually either drill or melt our way and put the submarine down there. And who knows what we are going to find. So I was dreaming one evening, so well, we might find something which looks like this. And this is from the Caribbean. We might find something like this. And, you know, it's not impossible. You know, it's maybe a little far out. Maybe I was dreaming too much. But I wouldn't be surprised at all if we get into the ocean of Titan and we find some kind of life, maybe not like this, but, you know, you can do a bet. And that's not very far for the younger people that probably will be during their career that will be doing that kind of emission. And even here on Earth, the reason I say that's not impossible is when you go deep in the ocean, you know, as you go, like, for instance, where you find thermal vent at the bottom of the ocean, where there is no sunlight, but there is heat, you know, which is being emitted from these vents, you actually see life in there. When I was in school, you know, the age of some of the young people, everybody was saying, like, biology, you need sunlight, you know, for life. But it turned out you really don't need it. You need heat, you know, and organic material, and you can generate life. So it's very possible we can find life in the Europa Ocean. Now, let me come back to Earth and tell you a little bit about how, kind of what put me on track to being the director of JPL. And when we started launching the shuttle, the first 4 shuttle flights were supposed to be completely empty, you know, because they just wanted to test them to make sure they work. Then somebody came with an idea. They said, well, what if we put something in them? I mean, something which is not, you know, maybe we can put something risky, you know, in them just so we can fill them. So NASA, that's the typical thing. They made an announcement of opportunity. Lots of people proposed to it. So at that time, I was in my late 20s. So me and a group of other young researchers at JPL with some help of some more mature people. We went ahead and put a proposal for an imaging radar. And guess what? We got selected. So here we were saying, God, we are on the first shuttle flight, which is taken on, and we're a bunch of kids. But that's not unusual, at JPL. And that instrument, and that flight actually led to multiple, radar flight on the shuttle. In fact, 5 flights on the shuttle. And as I told you earlier, these radar instruments get you images very similar to cameras, except they do it day and night, or they do it if it's cloudy or not cloudy. And this was one of the first images we got from it. This is a radar image taken over Egypt. And the picture at the top is a camera image taken over the surface. And you look at the bottom one, and it looks like there is a river flow from it. So we were completely shocked when we saw that, because all the geologists who knew that area said, there's nothing there, it's only sand dune. Well, what it turned out then when we did another flight, this is another more clear example. You see the radar image at the bottom here, the visible image at the top, and you see this river that you don't see up there, you only see sand. Well, what it turned out, after that became kind of obvious, what it turned out is actually the radar is penetrating below the sand and imaging old drainage channels which existed many thousand years ago. So that got all kinds of excitement. It got front cover of Scientific American, front cover, of Science magazine. NASA was all excited. And particularly in here, I remember very clearly at that time, Bruce Murray was the director of JPL. So when we started doing the experiment, Bruce said, oh, I don't want to pay attention to you guys. This is high risk. We are doing it, just to fill up the shuttle. Well, a couple of weeks before the launch, he calls me to his office and he says, guess what? NASA administrator is having a hard time justifying funding for the shuttle. So he said, it better be successful because I want to show, the Congress that actually, the shuttle is useful. Well, fortunately, it was successful, and that got a lot of attention. And that, as I said, it led to 5 flights with more and more sophisticated kind of instrument. Now, like typical Caltech scientists, because we always are in heaven, we had to go and verify that what we're seeing are really actually buried channels in there. So we actually did an expedition, to Egypt, and it was a little bit of a challenge because this area was about like 300 miles away from any inhabited place. So you cannot fly there and go to the nearest Earths and rent a car and drive it. So we had to organize a whole expedition. So it was a group of people from USGS and JPL, a group from the Egyptian survey, and we had to take like 30 people with us who were workers, to support the logistics, the food, the tents, and then for them to dig, to actually do trenches so we can see that actually were riverbed. And you can see the tents in the back. And here I'll tell you a little interesting story. It turned out to get fresh food, because we were going for like about a month. To get fresh food, the Egyptians, who are very experienced, brought a bunch of ducks, because it turned out that ducks actually survive the heat wave. So we had cages and cages of ducks being transported with us. And they were all sitting put where the cook tent is. So we were having ducks every night. So one day I asked the cook, well, how can you sleep? Ducks are so noisy. How can you sleep? He said, oh, it's no problem. Whichever one is the noisiest, that's what you get for dinner. And then he said, you'll be amazed how quiet they get, after a while. So anyway, since that time, very rarely I eat ducks because we had 30 days of having ducks in every possible, combination. And we got, not at that trip, but another trip when we were back close to the inhabited area, we met, people were very welcoming in there. And then we did something similar in Oman, because also we saw indication of old ruins, in Oman. And this one was taken in Oman. And we found what we think is an old city called Ubar. So when you go home, Google Ubar, and now it's becoming a major tourist area after we're done there. And one thing which is interesting around these riverbeds is because people said, you know, when the rivers were flowing, you know, people used to travel, the caravan used to travel along the riverbeds, you know, because there was water in them. And as a matter of fact, we saw indication of human inhabited, that's a spearhead, you know, from about 7,000 years ago. And I have a bunch of other ones here if you want to look at them. And the way we dated these is because also we found ostrich eggshells, because supposedly the caravan, they used to use ostrich eggshells, which are pretty big, to carry water in them. And ostrich eggshells, you can date them because they have carbon in them. And they were dated to be about 7,000 years ago. So that's not a long time, you know, ago where these rivers, you know, actually were flowing. That's about a couple thousand years before the pharaohs. So that was a very exciting. So the reason I'm telling you this is particularly for the young people, to tell you being a scientist is a lot of fun because you can do all kind of things. Now, then after we flew a couple of these things, then one day, literally we were in a meeting and we were kind of brainstorming. And then one person said, well, you know, how about if we add a boom, you know, to the shuttle and then put a receiver on the other end, and this will become like an interferometer. Now, some of you have taken physics classes that's similar to the Fresnel interferometer. If you punch 2 little holes in a piece of paper, you shine laser on it, and you have a surface behind it, you see fringes. And if the surface is flat, the fringes are parallel lines. If the surface is kind of wrinkly, the fringes will follow the topography of that paper. That's how interferometry works. So we went to NASA, as a usual thing, and we tried to convince them to put a boom, you know, on the shuttle. And the first reaction of the safety guys, are you kidding us? What if you cannot retract it back in? How are we going to bring the shuttle? But the astronaut in their typical thing loved these kind of adventurous things. They said, look, if you cannot retract it in, we will go out in a spacewalk and take the screws up and dump it, you know, from that. So finally, we talked them into it. And this is a boom that we put. It was like about 60-meter long boom. And that's as it was deployed in space, taken from the cabin shuttle. But the important thing about it is you see a lot of these 3D images. So when you look at your topography map today and 3D images on your, they were all taken from that mission. So in basically 2 weeks, you know, we mapped most of the world between plus 55 degrees and minus 55 degrees, which was the inclination angle. And we generated topography directly digital on doing that. Before that, there used to be hundreds of people who sit down, take stereo images, and sit down and try to draw contours. I mean, it was really an extremely tedious process that people followed for hundreds of years. And here, because of somebody came with an innovative idea during a brainstorming session, we were able to generate that directly in digital format. So now that's how they are being done. And now there are more advanced satellites, you know, which can do that. Then somebody came with an idea. He said, well, what if we fly multiple times? And what if there is any change in the surface? Can we measure that? Well, it turned out actually we can do that. This is Los Angeles Basin. And what you are seeing now, the scale you see it up there, we're talking about 5 centimeters. So you think you are sitting down and you are fixed on the ground. Actually, you are moving up and down. You know, and the reason that's happened is every time we pump water from the water table, the surface goes down a little teeny bit. And every time the snow melts in the Sierras and the water fills the water table, it pushes you back up a little bit. So we're actually, and now the state of California is using this kind of data in the Central Valley to basically monitor how much water is being pumped and to do more management, you know, of how much, you know, the farmer will actually pump, you know, water and try to predict that. So this is example also of this innovative thing. And then the next step, somebody came and said, and that was Mark Simon, a colleague of mine here who have done the previous one. And then somebody said, well, what if we take a picture today and an earthquake happened tomorrow? I'm not predicting that, but if something happened, and then we take another picture, And then we combine the two. Can we determine how much motion actually have happened? And that's a picture of an earthquake which happened in Turkey, a few years ago. So every time you go from one fringe to the other one, that means it has been displaced by about 5 to 10 centimeters, on the surface. And this is of benefit if we can do it fairly quickly and send it to the rescuer. So you can see places like this. That means there was a lot of motion which happened in here, and there are fewer and fewer motion here. So we effectively can now take picture of the displacement resulting from an earthquake. And not only earthquake, anything which changes the surface, actually you can see that. That's an example of actually where about the eruption of a volcano. People were able to monitor it as the volcano inflates little by little by little, and then it erupts, on doing that. So again, that kind of thing, in this case, we can predict an event might be happening and therefore notify people. The earthquake is a little bit harder to do that. And that's an example of the Kilauea eruption, not the recent one, but the one which happened in 2018, where we monitored all the changes which have happened and the displacement which have happened before that eruption. So that gives you a flavor of the kind of thing. And all of this being done from space. And we're talking about displacement of few centimeters, that much. And we can measure it, with this kind of imaging radar. Now, the reason I told you all this, just, for the fun of it and tell you about the advances, but just a few months ago, JPL launched a satellite called NISAR, which stands for NASA India Synthetic Aperture Radar. It's a joint effort with India. And what that satellite is going to do, all what I told you before about every 6 days. So it will be mapping the whole world every 6 days. So we can get basically the heartbeat of the Earth. Will be monitoring the changes which are happening, every 6 days over years, from now. So this is going to revolutionize, basically how we understand our planet. It could be from tectonic displacement, earthquake, volcanic eruption. You can measure as the trees grow, that changes the surface. So you can measure how much they are growing. You can measure if there is moisture in the ground, because the soil actually inflates a little bit when it's wet versus when it's dry. So you can measure, landslides even before they actually happen, because you can see slight displacement in them before they actually occur. You can see, avalanches again because it weakened, the ground is weakened a little bit. And because we are talking about, as I said, about centimeters, things that you don't perceive in your eye. So that's going to be the case over the next few years, that we'll be able to monitor that. And I picked one example. This just was taken a few months ago, where you actually see the slides. That's in Alaska. You can see the slides in here, capital relative to this place. So that's going to happen now on a routine basis. So hopefully that illustrates to you the kind of advances and discoveries that have been happening. And I always like to show this as my last slide about their mighty things, because that's the kind of things that we do at Caltech, that we do at JPL. We don't take the easy way. We look at what are the most challenging things and actually go and do them. And yes, every once in a while we fail, but that's how you learn. It's through failures you actually learn from it. This was taken from a quote by Teddy Roosevelt, which I love this quote. So it's all over JPL for the last 15 years. So hopefully that gave you a flavor about some of the discovery and all the excitement of being in this field. Now, before we take any question, I'm going to show you a short video, and which is not exactly related to this, but last month, a researcher who used to be at JPL by the name of Eric Fossum actually received what's called the Drabel Prize from the National Academy of Engineering. And that's the equivalent of Nobel Prize in engineering. And he received it for a simple reason. All have an iPhone, and you all have a camera. You wouldn't buy an iPhone. Almost most of you would that the focal plane CMOS was actually developed at JPL. was developed for our telescope. So we wanted to have a super thing. Very power and very hot. And then it goes to the I can put that in my computer. And that's how it ended. So that's an illustration for you of how space activity actually will allow you to advance technology. So that kind of detectors are being used in many telescopes. I didn't talk much about astrophysics. Oh, I lost my mic. I think I was too excited about what I'm showing you. So anyway, Fred Farina, who is here at Caltech, is putting together a video about that, not discovery, but development, for it, which is going to be made public in the next week. That will be on YouTube. So we asked him to do a 2-minute version just to give you a sneak preview about that. So hopefully, I have not seen it myself either. Okay.
NASA was launching spacecraft with cameras, of course. And those cameras built on CCD technology were quite large, like the size of a small refrigerator. That was the problem I was faced with.
The message from the NASA administrator was better, faster, cheaper.
I had no idea how massively useful or ubiquitous the technology would be.
And we got the first chip back and it actually worked. And it was like, oh my God, this is fabulous.
Once it worked, it was wonderful because now you were not at the mercy of the domino of passing the charge from one device to the other over a long chain. That made things much more complicated in the long run.
Behind me right now, we're receiving data from the rover on Mars.
Right three!
Our first commercial success was with Logitech, which were the little small round cameras that went on top of PCs.
This is an old school Logitech webcam from about 1999.
Now, of course, we Zoom every 5 seconds, but that was the beginning of video conferencing.
Now, a new generation of phones is about to hit the streets, and these handsets can send not only text, but take and send pictures as well.
People thought, why would you want a camera on a telephone? The phone is to call people, the camera is to take pictures. It was the first startup out of JPL commercializing IP that was developed at Caltech and JPL.
No one would have believed in day one when all this happened. And we talk about this literally on a weekly basis here.
Our job is to try to take these inventions and turn them into commercial products that can benefit society more directly, above and beyond research papers.
I consider myself to have the entrepreneurial spirit, but entrepreneurship also requires an environment that is conducive to that.
It's going to take 5 to 10 years for the technology out of the lab to be developed.
It's key for universities and science institutions to help potential entrepreneurs. If you want tech transfer to be successful, give it to the engineer, the scientist that has the fire in the belly that's going to make it happen.
If we could pull up a selfie, I don't know, Kim, if you're able to pull up a selfie from the photojournal, maybe?
Fresh from Mars.
Yeah.
So hopefully that gives you. So with what you heard today, that give you a couple of things. How much investment in science and technology could impact our life? Yeah, we do that for knowledge, but it's way beyond knowledge also. It affects our day-to-day life and our economy. That part of the reason that our economy is ahead of everybody else is because of the investment that was made over decades in science and technology. And the other thing, hopefully, it show you about the excitement of being part of Discovery. Thank you very much.
So we can take a few questions for our speaker. If there are any questions in the audience. Yes. Go ahead and ask your question. I'll repeat it for the audience.
Oh, here.
What? Pardon me.
Thank you so much for sharing some of your vast knowledge with us tonight. My question is, what would be your best guess at when a human being would set foot on Mars? Thank you.
But like somebody said, it's kind of hard to predict the future. You know. Now, for Mars, I would say two things. Technologically, we know how to send a human to Mars. But there are a lot of other factors. I mean, it's a huge engineering investment. And also imagine yourself with your best friend sitting down in a capsule for 9 months to get there, spend 9 months there, 9 months to come back. I don't think you'll be friends by end of that. So there are, and the reason I'm saying that, I'm not doing it as a joke, but there are a lot of psychological and physiological challenge. Now we are progressively doing that, you know, learning, you know, from the space station of people sitting there. So if I have to guess, I would say by the end of next decade, you know, that I think it's possible to be done, but it's going to require a large, not only US, but international investment in doing it. And there is one additional thing, again, as I said, now that I'm retired from JPL, so I can say anything I want. People always ask me, would you love to go to Mars? And I tell them, no. I love it here. You know, the beautiful trees, the flowers, the environment we have. Mars is great for scientific investigation and learning about how solar system evolved, could there have been life, but it would not be my primary destination for holidays.
Additional questions for our speaker?
First of all, I'd like to thank you for your amazing presentation. And you mentioned how we can potentially find life on Europa under the thick layers of ice. And my question is, how can current and future generations of scientists conduct a mission to potentially mine these thick layers of ice sustainably without harming those potential lives or organisms? Thank you.
So the mission, sorry, I missed about that.
So how can we safely mine the ice without disturbing any kind of life under the ice?
I see. Well, all of this is being looked at, okay? So it's not straightforward. And we're always very conscientious about will we disturb whatever we are going to look for. You know, for example, in the case of Mars, we really work hard on cleaning our spacecraft. So we don't take microbes with us and then come back and say, look what we found there, and it's something we took with us. So the same thing we'll have to do, you know, also for Europa. So we don't disturb or impact the life on it. Now, the other question is, how are you going to get down to that thing? And there are two techniques people are thinking about them. One is doing drilling like the oil companies do. The other approach is actually putting in a small nuclear object and it will melt its way, a hot object melts its way. But your point is well taken. I mean, we have to figure out a way to make sure we don't disrupt, you know, what we are looking for. And the other part, which my wife always reminds me, she's my conscience, is we tend to look at life which looks like us, because that's the only life we know. Life could be very different. You know, that's something that we haven't thought about. So you just have to keep your mind, you know, completely open about what are we really looking for.
We can take one more question before we switch to our panel. Don't worry, there will be plenty of time.
Later because we have.
But our online audience won't be able to hear.
So there will be time.
Can you pass this down?
Again, thank you very much. I guess partnering with his question, does it even make sense to send humans to any of these places, considering how far robotics has come and all of those things? Why would we even bother sending humans to do that work?
Does it make sense to do that?
Yeah.
Is that what you're asking?
Right. Does it make sense to send humans when we can do it robotically?
That's also a very good question to do that. Now remember, I come from a robotic, you know, lab, but I do favor sending the human because human I mean, two reasons for it. One, humans are an extension of us. I mean, we don't want to explore, and then having human will kind of make part of your feeling. I mean, I remember, maybe you are maybe a little younger than me. I remember when Neil Armstrong landed on the moon. I mean, it was something mind-boggling that we have a human, which actually, I was sitting in the student houses, here at Caltech when that happened. The other thing, no matter how sophisticated we get our rovers or helicopter, still human can make judgment much quicker. Even with, with artificial intelligence, still human can make decisions, much quicker and much faster. And then the other part is, and maybe I shouldn't make that judgment, particularly in front of young people. It's kind of, it will be like part of us that is traveling when we have a human. Now, for some people, a rover could be part of us also, because it was built by human. But your point is very legitimate, because sending a human is extremely expensive. I mean, we can send 50 rovers, to Mars for the cost of one human mission. But you have to take that additional factor, which comes with it.
Let's thank our speaker. Okay, so now is the point of the evening where it's kind of a choose your own adventure. We have telescopes set up outside. I'm told that we can see through the clouds, at least for viewing Jupiter and the moon and some other, maybe some deep sky objects. But at the same time, in about 5 minutes, we'll set up the table here and have a Q&A panel in here over the next 45 minutes or so. So you're free to go back and forth, stick around here and ask questions of our speaker, myself, and other planetary scientists in the department, or go check out the telescopes or vice versa. But thank you for joining us, and we'll see you in a month and a half at our next one.
Yeah, I guess we have everybody here. Yeah. So yeah. If you want to sit down, you can bring your chair. Yeah, there is a bunch of them here. That's a hand axe. Or that you use it, to do that. Yeah.
Really one of the best talks we've had.
Sorry?
It was one of the best talks that we've had.
Oh, thank you. Thank you. Oh, okay. So we'll bring. Do you mind sitting there so we can take the chair? Because we can't. Or maybe you can move. Oh, okay. Oh, thanks. Say hi. How are you?
Mr. Elachi, 31 years ago, I was your student.
Oh,
at
yeah, no,
Indiana
no, I
School.
remember. Yeah,
Remote sensing.
Yeah, good to see you.
An honor to see you again, and
Oh, good to see you.
what you're doing. It's
Sure.
Thank you so much
Oh,
showing
sure.
the video.
So it works well?
Great.
Yeah,
Yeah, yes,
that's good.
absolutely.
Hi, I'm Rob Clyde.
Oh, yeah,
I'm
yeah,
the
yeah.
Rob is the
filmmaker.
producer.
Yeah, yeah.
That was amazing. Thank you so much for setting it up so well.
Thank you. Thank you.
I
Yeah,
did-
thank you for doing it so quickly, the video.
That's great. The whole video is only 10 minutes, but I think people were.
Yeah, I saw them
taking,
taking
yeah.
pictures
Yeah.
of
And so next week, you'll be getting emails from
them.
Caltech Communications saying, hey, share this, promote it. Let's
Oh,
get
okay.
people to watch
Very
it.
good.
Anyway.
Hey,
we'll
how
try
are
to
you?
continue.
Say hello. Hey, how are you doing?
Good.
Good to see you.
You still have your 280?
No, I sold it. I sold it to somebody at JPL because it was getting harder to get in and out of it. It was so low. So now I have an SUV, which is much easier. Yeah, good to see you.
You remember me?
Oh, yeah, no, I remember you.
Gunning.
Yeah,
Thank you for
sure. Okay. So he wants to put the name. Hey, good to see you.
What a wonderful
Yeah.
talk.
Thank you
so
thank
much.
you. Well, you guys
How are
made
you?
all of this happen.
Thank you for
Sure.
bringing.
Take care. That's great. I don't have to be behind the table.
All right. Thanks for sticking around. So this is our Q&A panel. What we'll do is each give a brief introduction to who we are and what sort of science we work on, just to give you an idea of our expertise and how well we can answer the various different questions that you have. So I'm Dr. Cameron Hummels. I'm a research scientist here. I primarily do computational modeling of galaxies and follow their formation and evolution in a computer simulation to compare against observations.
Hi, my name is Maria Camarca, and I was a graduate student here, and now I'm a postdoc in planetary science. I'm really interested primarily in Jupiter's moons that I study using telescopes in both the infrared as well as the radio to do thermal studies of their surfaces.
I should also mention that Maria was just awarded a National Science Foundation National Postdoctoral Fellowship today.
Thanks.
Hi, everyone. My name is Riley Davis. I am just about to defend and finish my PhD here in planetary science. And I use telescopes both from the ground and in space, so things like the James Webb Space Telescope, to look at icy moons from Jupiter all the way out to Neptune and try to understand how they formed and maybe what's in their oceans and things like that.
You know.
Okay, and now we open it up to you guys. I already see a question from our young regular here.
Does Mars have layers of atmosphere like Earth? And if it does, what is it made of? And how does it change the way Ingenuity flies?
Yeah, so Mars, the composition of the atmosphere is different than ours in terms of what the main molecule is in the atmosphere, which is mainly CO2. So again, I don't think Mars would be a great place to lay a beach towel out and try to have a sunny, breathe easy day because it's not the type of air we can breathe. In terms of what the layers in the atmosphere are, there are some parts of the atmosphere where you can have aurora, like what we see on the Earth, like the Northern Lights. You can have that at different layers. They can be different colors. So there are some things that can be similar and then some things that are different, like what it's exactly made of. But that's a really good question.
I'm sorry, I'm going to be a jerk because this question is for Charles. What would you say were some of the biggest, what were some of the most difficult parts of being director of the lab for so long and through such a time when there was so much going on?
So I wouldn't say that it's one exciting. Everything is exciting. Every day, whenever
Questions? I'll hold off on you.
Thank you. I wanted to ask, is there anything that you all want to say to the younger audience here that are like interested in pursuing a career in this field, or just pursuing anything in this field?
Oh boy, I don't know. Advice that we have for people who might want to pursue a career in astronomy or engineering or space physics. Stick with your math classes, learn to code. These are all very, foundational skills that allow you to do the exciting and the interesting stuff. And sometimes the details can be a little bit tedious, but ultimately it gets you. It's like some of the things, you might want to kick the door at the end of the day, but ultimately the rewards are well worth the challenges that you face along the way. Junior in college studying computer science. Good work. I studied CS as an undergrad too, and it was very worthwhile and helpful.
Yeah, I think at your level, as a college student, my advice would be to get involved in research in whatever ways you can. Find a good mentor and see if they have kind of projects you can have some fun with, and see if it's something that you like, because I think it is different from what maybe a lot of people think, and you may absolutely love it. But it's good to know that while you're still in college.
Adding on that, I have to give you one sentence for so Oh, okay. So try to do research, because one of the things we look at, when we are admitting students, or if I'm looking for people to work with me on a PhD, is have they done things other than just classroom? Have they done something innovative? Have they done the research? Because that's what you need to be able, to kind of move ahead in your life. You don't want to be sitting down just doing homeworks and taking exams. And try to broaden your background. I require all my students and postdoc, I require them to go and take a class in something completely different. If they are in EE, I encourage them to go and audit a class in planetary science or in mechanical engineering. So you can broaden your experience, because you really can never tell where you are going, to what would you love doing. I will give you one example. Our daughter, she did her undergraduate in biology. Then one day she came and said, I don't want to be working in a lab, after she got her BS. Then she helped some people in Africa on building homes. So she decided to go in architecture. And then now she is working with the Audubon Society, looking at the environmental thing. She's a director in Southern California, Audubon Society. So life can take you in a different way, and it's good that your mind is open to different possibility, and if a door open to you, take the opportunity to do it. I didn't plan on being the director of JPL when I was your age. I mean, I didn't even know where Pasadena is, other than, and I tell people the reason I ended coming to Caltech versus MIT and Stanford is when I looked at the map, so Pasadena, then I saw Hollywood next to it. So, oh, that's where I want to go. So So anyway, I mean, you can never tell what life, I mean, prepare yourself and be open-minded on what you would like to do.
Any additional questions? I'll
He
come
has
back to
another
you.
question.
He does, but there's
Oh.
another gentleman back here.
Are there any other auroras in our planets in the solar system or moons?
Yeah, that's a great question. So there are other auroras on different planets. Jupiter, for example, has its own aurora. But even little moons in our solar system can have their own aurora. So Jupiter has 4 really big moons. And we now know that on all of them, they all have their own little version of the northern lights. Ganymede, which is one of them, has northern lights where the name suggests, for example, at its north pole and at its south pole, because Ganymede has its own magnetic field, kind of like the big terrestrial planets like the Earth do. But some of the cool things that happen on some of the other moons, which don't have, you know, a perfect little magnetic field of their own, is you can sometimes get northern lights really near the equators of those moons. But the auroras come from oxygen atoms, so it's the same red and green that we're used to here on Earth, but just in very thin atmospheres. And I'll just add that the way we see those auroras is kind of a really cool trick that you can play when observing, is that to see the aurora, astronomers wait until the moon, that little moon, is in Jupiter's shadow. So we wait until the lights are completely off on the moon, then we take the measurement. So I think it's just a very just a very elegant way to do science, the aurora science that you can do for the moons. And we learn about their atmospheres that way. We learn about their surfaces, but pictures of auroras on other worlds in our solar system, I think, is just cool and beautiful. So feel free to look up pictures or that type of data if you like.
And just to add on that, if you haven't tonight, Jupiter and those 4 massive moons are visible through one of the telescopes. So you can't make out the aurora, unfortunately, but you'll see Jupiter, the disk of Jupiter. You'll see maybe some banding of its various bands. If you're lucky, you can see the great red spot, but then you'll see what look like 4 stars in a line. Those are actually reflected sunlight off of these 4 moons. And because they're orbiting in a plane and we're looking edge on at the plane, it looks like these 4 points of light in a line adjacent to Jupiter.
While he's running there, I want to add 2 things for you, here. One is, like you said, they're mighty things. By that, what I mean is, don't take easy way. Take tough things. That's how you learn. Don't take an easy class where you get an A. That's okay to take a tough class and get a B because you learn from it. And don't be discouraged if you fail. I showed you about all the successes here, but some of my colleagues said, we did crash some spacecraft on Mars. but we learn from them. That's how you learn and you get better on doing things.
Thank you for a very good talk. My question is, so all this space program are very expensive. So is there any coordination between US, Europe on who going to do what to cover all different open question, or more in competition? Now, my question is Europe, China, Russia, Japan, any country we coordinate to explore the universe,
Coordination, other nations.
Yeah, is it more
or more a competition?
Yeah. Now, as I kind of hinted a little bit, every mission we did at JPL had an international element in it, and we do coordination, with other nations. Like this last mission, the NISAR, the I is for India. So it was jointly between us and India. Every instrument I had Italian collaboration. We had many missions which we coordinated with the French space, agency. Now, to address the tricky ones, we do a lot of collaboration with ESA, actually coordinate mission. For instance, a mission going to Europa now is coordinated with a mission that ESA is doing, called the JUICE, heading in the same direction. but it's going to explore another one of the satellites. Japan, we do a lot of work with them. Now, China and Russia are more tricky to do that. First, in the case of Russia, we still work on the space station together. But after the Soviet Union collapsed, for planetary, the Russia program has disappeared. There is effectively no planetary or very little. China is a little bit different. And I did a lot of collaboration with China. Matter of fact, I did a lot of field work in the early days from some of the missions you saw here. But the tricky situation with China is that their space program is jointly with the military. So it's not like what we have here, where we have NASA, which is civilian, and the Air Force or Space Force now have their own program. So it gets very tricky because it has military implication, transfer of technology. And it will be great to collaborate if we can find a way with China, because they have been doing some amazing things, in there. But politics get involved, in doing that, again, because of the military aspect of it.
Do the laws of physics apply to other planets? Like if I bounce a ball on Mars, will it bounce back up?
Great question. Yep, so the laws of physics do still apply. But on Mars, if you bounced a ball, it's going to go a lot higher than it does here on Earth, because Mars doesn't have quite as much mass. And so it's the exact same laws of physics. Gravity is going to work the same way, but it will get to go a little bit higher. Or if you wanted to run on the moon, you could bounce, way up high with every step.
Before we take our next question, I should just mention, if people,
there's a hat there.
There's a hand on this side. The main thing I wanted to mention is if you want an opportunity to look through the telescopes, they'll be doing it for another 10, 15 minutes or so, and then they'll close them down. So if you haven't, I encourage you to go check it out if that's a priority for you. I think it's cooler what we're doing in here, but.
Okay, then I'm glad I can ask this quick. I'm someone who has always been a space nerd since I was a kid, but I went a very different career path and I don't do anything science related. So I am kind of a casual consumer of, space exploration, news and things like that. Do you have any favorite podcasts, documentaries, Substacks, or anything that you think I should have on my radar to digest the amount of news without being kind of boots on the ground?
Good media to digest different space science content in general. Sure. Ooh, what do you think?
The Planetary Society has one that I think is a pretty good,
Planetary radio.
One thing you might do, what are you majoring in? Or what are you studying?
I work in fashion business.
Oh,
okay.
No, I mean, what I was going to say is, the JPL has a summer program. And it's not only for engineers and scientists, because there are positions for people who are accountants, people who are in public relations. Spending a summer at JPL for somebody who's a space nerd, like you said, will be a lot of fun. I mean, I had a lot of friend kids who came and work in public relation or something. So think about that. That's one part. It will embed you in that kind of an environment.
I feel like one approach that might work is that, for example, maybe instead of only relying on like the science section of a newspaper, thinking about a couple universities whose astronomy programs or planetary science programs you like, and check their news updates. So it's like written probably closer to the team doing the research in some cases. Now, a lot of news organizations have like very thoughtful science programming, of course. But if you want to hear like planetary science news, like Caltech has a news section as well. So that could be another way, at least when I'm trying to get the temperature of other science that is like outside my expertise. That's where I usually go. Yeah, so that's one thought.
There's one that I like. Universe Today is a web-based kind of science, but astronomy, astrophysics, space science, topical place that covers a lot of relevant stuff. And for reference, it's also, if you go to Astronomy on Tap, I get a lot of my content from there. So that'll be in the pub trivia questions. So study up on that, and maybe it'll give you a heads up on the pub trivia.
Since we've just had a question from somebody who's not a scientist but is interested in what we do with planetary science, are there any citizen science opportunities that you'd like to mention that somebody who's not a professional scientist but is still interested in science might be able to participate that way?
Yeah, so for those unaware, there's a kind of a activity called citizen science, which allows non-scientists to contribute towards the scientific endeavor. NASA has a number of them. There's a number of different disciplines, but kind of one of the primary places that you can go is look up, it's called the Zooniverse. So like ZOO Niverse. And there are maybe 40 different opportunities, everything from going out during a meteor shower and counting the number of meteors that you see that can go back, if hundreds of people around the globe do this, it provides scientists with much more in-depth, detailed information about meteor counts from different locations on the Earth that we can track back to how intense that storm was globally this year versus last year versus the next year. People do things. There's one called aurorasaurus that's for again, categorizing aurora and northern light activity and the intensity of that. There's one with sunspots. There's one with all manner of things. There's one with being able to identify, like getting real telescope data and morphologically constrained galaxy shapes in a way that scientists don't have enough people to go through and do this task. And this feeds back into real science. And so you're really contributing and really it helps the entire field. So, and you can be on papers because of your contributions that you've made to the field. Zooniverse. If you look up Zooniverse, or if you just look up NASA citizen science, that'll also have some options and opportunities. Yeah.
Thank you. With some of the successes of especially the commercial space companies of the past 5 to 7 years, has that fostered any significant cultural shift within JPL, like break it faster kind of mentality, if things accelerated? And have you determined if, or can you sense any of that within the organization?
I guess that's for me.
Yeah, I think so.
Now, let me tell you at least my personal philosophy on, industry, JPL, NASA. Basically, NASA and JPL, we are in the business of pushing the frontier of technology and science. And then once we develop that, we want to turn it over to industry, so they can make a business out of it. So we actually favor transferring knowledge, to industry. And when you are doing fundamental research and pushing technology in the limit, the mindset is a little bit different. I mean, let me give you one simple example, personal example. After I retired from JPL, I was asked to be on the advisory board of Northrop Grumman. So I went to my first meeting and the CEO was sitting there. And one of the researchers came in and presented something to the board on this. And the first question the CEO said, is this going to make us some money? And I looked at her and said, in my 50 years at JPL, I never asked that question. So they think very differently and properly. I'm not saying it, I have stocks in companies. I want them to make money. I don't want them just to, at JPL, we never think about that. So the mindset is somewhat different, but we work together because our success, part of our success is to actually move the knowledge and technology, to industry. And the industry tend to think in the short term. Their horizon is typically, not always, typically 5, 6 years. I'm sure at JPL now they are thinking about mission 20 years from now and technology needed 20 years from now. So the two have a different purpose. But we can learn from each other. I'm not Industry tend to be much faster and willing to take more risk than we tend to do at JPL.
Question for Dr. Elachi. What is one of the most meaningful achievements that what is a most meaningful achievement to you in your career, and what do you most look forward to in the next 5-10 years?
Well, I mean, no, I would say people ask me what's the most exciting things for the next decade. And I would say number one, if we find life somewhere in our solar system or find habitable environment, be it Mars or Europa, because that will completely change our thinking, about what life is. The other one is exoplanets, finding a planet which is similar to Earth around another star. Now, always people ask me, do I believe there is life in the universe? And my answer, absolutely. There is no reason why life only exists here, but I cannot prove it for you. And detecting a planet which is similar to our planet, a similar environment, and so on, or if we see somebody waving at us and say, I don't think that will happen in the near term, but really that will change our thinking about what's our role in the universe. So these are probably the two, I would say, most exciting thing. And all of this could happen in the next 5 to 10 years.
Hi there. So at NASA, I'm seeing a culture of integration of knowledge. And recently, I've been looking into the ancient knowledge transference system. So from the ancient Greek to Islamic, and then into the Latin Europe. And it was intriguing to see that arithmetics, geometry, and music together with astronomy has always been together. And I'm just wondering if there is any connection, because from Kepler's, he wrote a book about orbital mechanics and music. And then there was Pythagoras' music of the spheres. So I'm just wondering if there is any clear research going on about the relationships between ratios, music and mathematics.
Connection with music. But let me answer your question more broadly, and then you can add your thing about connection between space exploration and art in general. First, you might know, or you might not know, at JPL, we have a group of 12 artists who work at JPL. And their role is to actually how to explain what's being done to the artistic world in general. They do displays in museums and vice versa. They sit down with the teams, which are doing design of new mission, and they bring their perspective, as artists to it. The same thing, maybe it's not exactly the same thing for music. Every time we wake out of our rover, or we used to, we always transmit some music in the morning to them to wake them up. But I don't know if we do it at the present time, but that used to be common before. And the last thing I want to mention to you, because I felt it was great, is we had a poet in England. He was he fell in love with spirit and opportunity. So he was regularly sending to us poems, related to his love about spirit and opportunity. And when they died, he sent us a eulogy, for them. So yeah, I think, and I can tell you, maybe Cameron is better at it. Every time I look at some of these Hubble images, or recently I was looking at the image of the Rubin telescope, I mean, I find them like a piece of art. Before I think of them as science, I think of them as pieces of art in doing that. Want to add something?
The only thing that I'd add is I think the subject matter that you mentioned, music and mathematics and arithmetic and astronomy, these are all tied together as mathematically based. And so I think the traditions that you were describing from, cultural centers, the Greeks and the Romans to the Arabs and then to Western Europe, it's largely following these paths of connection to mathematics at its root. But absolutely, I agree with what Dr. Elachi was saying as well. Okay, additional questions. I'll get to the back. I've been doing a lot of stuff in the front, so get to you guys. And then I'll get to the middle too. Don't worry. We'll get to all the people.
First off, thank you all for being here. I have a question. Sorry if this has already been asked, but in a perfect world with like no engineering restrictions, what's a dream piece of kit or dream piece of technology or specific instrument you'd like to see in a future space mission?
A dream piece of technology on a space
Okay,
mission.
if it's like total dream, as in like not gonna happen, I would like to be in a spaceship that flies through Enceladus's plumes. Like,
Ooh.
yeah,
Oh, yeah.
like Splash Mountain type. We're going through.
But first,
Yeah.
introduce what Enceladus is to people.
Oh,
They
sorry.
may not
So-
know about the plumes.
Enceladus is an amazing moon. So it's a moon of Saturn. So oceans in moons is like a thing that happens not a few times in the solar system. The subsurface ocean actually pouring out of the moon is something we only see with like super certainty on Saturn's moon Enceladus, which has these cracks at the South Pole from which the ocean is literally pouring out, making a nice sparkly E-ring named for the Enceladus ring. So we've found organics in the plumes. The Cassini spacecraft that was mentioned earlier did itself fly through the plumes, but I want to fly through the plumes. So that would be my dream spacecraft, is me on spacecraft through plumes. So yeah. I'm kind of more serious
Again,
answer.
if we're talking about dream technologies to put in space, there's a hypothetical drive called the Alcubierre drive that allows you to essentially warp the space-time in front of you and behind you, that effectively pushes you forward in space, and you can potentially travel at faster than light speed. Not where you're actually traveling faster than light, but the space-time warping around you allows you to travel faster than light. So this is hypothetical, but it holds up according to Einstein field equations, which are kind of the governing set of equations for how things can move in relativistic space and gravity and all of this. We actually had a lecture, one of these lectures given a year ago by one of the young professors in the department, Elias Most, talking about faster than light travel using an Alcubierre drive. So I encourage you to go check that out. It'll have more information than I'm explaining here. But if we want fantastical technologies on our spacecraft, that would be one that I would vote for. The improbability drive. That's true. That's true. There's a lot of options. Okay, there's a question in the back.
You might leave a microphone in the back instead of having to run back and forth.
The last couple of years in particular have been pretty difficult to be working in science and also just at JPL. So do any of you, so for science or on the JPL side, do you have any advice for those of us who are early in our career and trying to just do the work?
Persevere.
Yeah. That seems to be a reasonable word. I was told I need to stick around until something randomly good happens, was advice from senior colleagues. So that's what I'm writing on currently.
Yeah, I mean, certainly funding opportunities have been more challenging as of late, and particularly in the fields of astronomy and astrophysics and planetary science. There are more and more graduates coming out with undergrad or PhDs in the field, and less opportunities at the high levels for professor or permanent staff positions. And that, coupled with proposed and actual funding cuts at federal level towards NASA, towards the National Science Foundation, towards DOE and other federal agencies, has been challenging for sure, especially in the last year or so. I'd like to think that those will not be permanent things. I mean, a lot of this is guided by political priorities, and those may change at some point. So at least, I mean, I don't say this as like, this is what you should do. I'm also facing these problems too. And what I'm kind of keeping my nose to the grindstone and trying to persevere for the next few years, and then see what opportunities are there. That's
yeah, let me answer it more in general term. Even that there might be a challenge in finding opportunities in astronomy or planetary or science. But if you go in that field, it teaches you how to be thinking critically, how to be innovative on doing that, which will serve you even if you end becoming a lawyer, like I said earlier. So it's really learning. This is something which will allow you to learn how to think critically and how to be able to make discoveries. So which benefit you across things. Many people I know who started, got their degree here at Caltech, and they ended working in Wall Street. There's something completely different. So don't think about it only, is there going to be an opportunity at Caltech as a faculty in astronomy, on doing that. So think about it in a broader sense, because it is challenging a little. Sometimes I do worry about generating too many PhDs, let's say in exoplanets, because there is a limited number of positions which is going to be there. And sometimes we might be doing a disservice for graduating too many students in a field where there are limited opportunities. So try to think about it in a broader sense.
You've been very patient audience members as I run around here.
Yeah, as you may know, the third generation of Starship is going to launch very soon. So what do you think about the Starship and Elon Musk's Mars immigration plan? And what do they learn from you and from the Mars mission of JPL? Yeah.
About Mars? Or Starship?
What do we think about the Starship, the third
you mean the
generation of
Starship
Starship?
SpaceX?
Yes.
Oh, you are talking specifically about that?
Yeah.
I have to be careful how I answer that. Look, I mean, there are different ways of going and landing on Mars. I think Starship is a big jump to do that. And despite I like Elon Musk, and I think he's a very innovative person. I interacted with him a lot when I was director at JPL, but he tended to way over promise. And in some situation, it's okay. I mean, it's good to see some people who are very visionary, to do that, to push the limit. But I think Starship is too big of a step to do that. Now, as you probably know, if you follow that, Blue Origin is also looking at a lander for the moon and a lander, for Mars. But it's more, I don't want to say traditional, because none of these are traditional, but at least it's a smaller step in that direction. So sometimes you have to be careful before you jump, before you go and do a marathon, try to run a 10K, first.
Question in the back.
I'm curious, maybe for the whole panel, what kind of brought you to the different subfields that you guys work in? I just feel like astronomy and space science has always been so broad, and I'm just curious if it was like personal interest or maybe a mentor or professor that you had in college that was researching a specific area that kind of brought you to where you are today.
I can start with that one. So I think for me, it was very much the mentors that I had along the way. So I started out in kind of pure physics. As an undergrad, kind of decided to also do astronomy, which is started out thinking about galaxies, so fairly far away from planetary science. But I learned to operate a telescope. And so there were different faculty members who were very happy to pay undergrads to go take data for them. And so got involved in different research projects and met just a fantastic mentor who was working on a little bit of exoplanet work and a little bit of work on Titan. And was in her office one day and she was like, I'm leaving tomorrow to go to Hawaii to observe on Keck. I don't want to stay up all night. Would you like to come to Hawaii with me and observe? And kind of stumbled into working on Titan and realized how much I loved planetary science because of that. And so it's, if you're in the field, as a student, just always be open to opportunities. You may not realize you're going to love a certain subfield, but if you get a chance to work in it, explore it and see, because you might be surprised.
So I got into planetary science when, as a biology major in my senior year at like a small liberal arts college, I learned that there was water outside the Earth. which as a college student learning that for the first time, like I felt completely stunned that that a discipline which focuses a lot on how water is useful for things like life, that I thought it was only the earth that had water. And I think I was just stunned enough. I was like, I think this is the type of question I want to spend the rest of my life thinking about. Not just that, but more broadly, like what types of planets are out there with water? How does it affect their geologies? So sort of water in the solar system was the gateway for me to a period where I spent as a post-bac learning research skills. But, you know, as a bio major, I hadn't had anything past calculus. So I remember when I showed up for a physics class to try to prepare for grad school, like literally all that was written on the board was like sine equals something. And I called my mom, I was like, I can't do this, which like, if you're not familiar, a sine function is just it's a very common type of function that you will use in all science and all math. But as a bio major, we weren't doing sine anything. Like when I reflect on some of the, just moments I had along the way, it just felt like it was too far away. But really for me, the motivation was, okay, this is where my intellectual home is. I love biology, but I had initially chosen it because I wanted to be a medical doctor. But I can't do blood. So I was like, I think those two things are not concurrent. So planets, bloodless, beautiful, really great. So that was sort of my entryway. Yeah.
Planets, bloodless and beautiful.
Maybe that's not the right marketing, but I guess I've said that. So.
I studied computer science as an undergraduate. I really like coding, and I really like software development and design, the creative aspect of it. But a lot of the applications for doing CS, at least 25 years ago, were not things that I wanted to do. I didn't want to work for an advertising firm, or I didn't want to do quantitative finance or whatnot. And science is a good way to continue that. So I got more involved in astronomy and physics and found applications for doing computational work. And my PhD advisor was a big player in galaxy evolution. And so you kind of fall in the footsteps of the people with whom you work and the mentors that you have. But it doesn't have to be permanent. You know, we can be involved in a particular area and then pivot and shift to a different area. That's, I think, some of the beauty of academia and some of the beauty of physics is, as Dr. Elachi was saying, you know, going through scientific background, it teaches you critical thinking skills and analysis that can be applied to many, many, many different problems. And you're not locked into being the thing that you studied as an undergrad or a graduate student or even a postdoc, or even junior faculty will change their areas and work on something almost entirely different. But the skills oftentimes continue across those spaces. Questions? Yeah.
I could probably look this up, but you know, at JPL, do they do basic science, or do you leave that to Caltech and the rest of the universities? Are you guys publishing a lot
publication, you mean?
And do basic research?
Oh no, absolutely. I mean, number one, you know, everything. Well, you saw the basic research about that short video. You know, they did some basic research on developing new kind of what we call CMOS. I don't remember what it stands for, which is a focal plane, you know, which is very light, very sensitive. And then that was published in the place. We have a number of people who are doing, let's say, modeling of climate change. You know, that's kind of basic. I mean, we don't do really basic in the sense that Caltech, the campus does. That's not as common to do that. So, but, you know, studying planetary atmospheres, doing new technology, electric propulsion, you know, system, a lot of work going on at JPL in doing that. And yet, publications are very important. So we do that. And there is a division at JPL, which is a science division, where it's mostly researchers doing, again, somewhat fundamental research in doing that.
Yeah, I certainly have a lot of colleagues in my field that I collaborate with from JPL who are working on cosmology, working on the early universe, working on cosmic microwave background or galaxy evolution. They're not just engineers at JPL. You have pure scientists, you have engineers, and you have the combination of both seeking to do pure research to understand the universe around us, as well as make telecommunications channels more effective or getting rockets to other planets.
Yeah, because one of the things, again, maybe you'll be interested in this, the way we define future missions, how do we come up with ideas for future missions, is we have scientists at JPL who work with the science community in general and with the Academy of Science and Engineering to identify what are the most critical scientific questions that need to be answered in the next 10, 15, 20 years. And then from it, then we backtrack of saying what kind of mission we need to do, what kind of technology we need to develop to be able to do those kind of missions. So it's really at the boundary between basic science and applied science.
I think we have time for maybe one last question. Okay.
So going back to the subject for advice for young aspiring scientists or astrophysicists, what would you suggest for expanding your research and findings from a local level to a greater audience or potentially the world?
You're younger age, you can answer that question.
How would you extend your research findings from a local audience to a global audience? I mean, really, in science, it's about publishing. It's about writing up your results into a manuscript and then submitting that to a journal. There are various different journals. There, at least in my field, there's the Astrophysical Journal, the Astronomical Journal, publications of the Astronomy Society of the Pacific, monthly notices of the Royal Astronomical Society. There's probably like half a dozen that you can submit to. And Planetary Science has theirs as well. Heliophysics has theirs as well. Each subdiscipline has a series of different places that you can submit your work. It gets reviewed by your peers, by scientists who work in your field to adjudicate how effective you are at doing the science that you're trying to do, and try and help you to make it better by poking holes into it and saying, oh, did you consider this? What about that assumption? So ultimately what comes out and what gets published is more rigorous than it might be if you were just left alone to write up the manuscript. And then that goes out to the world. And so if you write a paper, other scientists around the world will see it that work in your field and then reach out to you and be like, oh, this is really interesting. Have you considered this aspect of things? But really, it becomes global very, very quickly because of this kind of international publication method.
Yeah, I'll add on a humorous note. If you go too global, that could be a problem, as evidenced when the Journal of Fish and Fisheries reached out to my colleagues saying, your paper on Ganymedes aurora would be really good for our Fish and Fisheries journal. So when you reaching out to the journal is usually good. The journal reaching out to you, read it closely and see.
Yes, that's right. Going
Yeah.
to conferences in your field. So as I mentioned, in a couple of months, we'll have the American Astronomical Society meeting here in Pasadena, which kind of rotates between different cities across the US. And so there'll be a couple thousand astronomers in town, in Pasadena, walking the streets, looking for stars, but also spending their time presenting their results and their hypotheses and their analyses to colleagues within the field and making connections and networking. So it is really an international kind of global effort, and it's easy to meet other people from around the world simply by publishing and then discussing it at conferences.
And now that you mentioned that, I mean, if you are interested in science or astronomy, you might want to go to that conference and just sit down and see how do scientists, what they are doing, or if you are interested in music and so on, that's how you learn. You know?
Yeah, you can get entrance as a junior scientist. It's reasonably well priced. And so if you're interested, look up aas.org, American Astronomical Society.org, and you can find out about entry. Okay, that brings us to the end of our night. Thank you very much for sticking around. Let's thank our panelists. As I mentioned, next month we probably won't have these because I'll be traveling, but in late May and June we'll have a bunch of more events, especially to coincide with the American Astronomical Society meeting that's happening in Pasadena in June. So thank you very much and have a wonderful night.